Alright, hello everyone. Hope you guys are doing good. So today I will be discussing the solutions to Codeforces Round 774. This round was held yesterday night, and first of all, let's start by talking about the difficulty. According to me, I found the round to be slightly on the trickier side. I found it to be a bit difficult. Like the first two problems were fine, but even problem C was not that trivial, and even some experienced people got stuck on problem C itself. So yeah, C was not that good, and D was also very difficult, at least for me. So yeah, all in all, I found this round to be really hard, and that will be my take. So today I will be discussing the first four problems from A to D. So without any further ado, let's start with the solution to problem A. So in this problem, we have a sequence of n plus 1 integers, and for each I from 1 to n plus 1, it is guaranteed that either ai belongs to 0 to n minus 1 or ai is equal to n square. So this is what we have been provided with. So for every element in the sequence, it is either in the range of 0 to n minus 1 or it is equal to n square. Now the thing is that we have forgotten about the sequence, but we remember the values n and s, where n is the number of elements in the sequence minus 1 and s is the sum of all the elements of the sequence. And now we need to find the frequency of the occurrences of the element n square in our sequence, right? Yeah, so we need to count the number of elements in the sequence that are equal to n square, provided the values n and s is just the sum of all the elements in the sequence. Notice here that the constraints are not very small, so any kind of brute force solution is not going to work. So let's try to make some observations and try to simplify the problem. Right. So I'm going to make two very simple observations, and then this problem will become very trivial. So let's start. So the first observation here is that if the sum is like greater than n square, then there will be at least one occurrence of n square. So if s is greater than or equal to n square, then there will be at least one occurrence of n square. And this is my claim, and the proof is also not very difficult. Let's just quickly prove it. So the proof is that we know that s is greater than or equals to n square, and we need to prove that there will be at least one occurrence of n square. So let's try to prove it by contradiction. So we will assume that there are no n squares. So we assume that there are no n squares, and then we just prove by contradiction that s can never be greater than n square, right? So if there are no n squares, then all the elements are in this range, right, from 0 to n minus 1. So the maximum element here is n minus 1, and so let's try to find out the maximum sum that we can get. The maximum sum that we can get is when all the elements are equal to n minus 1 naturally, and there are n plus 1 elements. So the maximum sum is nothing but n plus 1 times n minus 1, which is nothing but n square minus 1, right? And this is strictly less than n square. So we have a contradiction now, because to begin with we assume that s is greater than or equals to n square, but here we are getting that the maximum possible sum is less than n square. So we have contradiction, so that means that there has to be at least one occurrence of n square. So this is the first fact, and the second fact is that if s is less than n square, then there are no occurrences of n square, right? This is a very obvious thing. Obviously, if s is less than n square, then how can there be n squares, right? Okay. So yeah, with these two observations, it is clear that if s is greater than or equals to n square, then there is at least one n square, otherwise there are no n squares, right? So with this, there is a very simple brute force algorithm that we have to solve this problem, and the brute force algorithm looks something like this. While sum is greater than or equals to n square, what you do is you decrease sum by n square and you increase your answer, right? So this is a very simple brute force algorithm, but notice that the constraints are large, so again this algorithm is not going to work. But let's try to simplify what this algorithm is trying to convey to us, right? So what we'll do is we'll try to represent these two numbers s and n square on a number line. Let's say this is a number line. So let's say this is a number line, and let's say that this is the number s, and let's say that this is n square. So according to the algorithm, what we are going to do is we are going to decrease from sum this value n square until and unless this sum becomes less than n square, right? So initially the sum is greater than n square, so we'll take this value and decrement it from sum. And now again we'll do this, and we'll keep doing this, right? This is what is going on. And once we are here, we notice that if we decrement s by n square, then s will become less than 0, and that is not allowed, right? And so here we notice that the answer is nothing but 5. And what this is trying to tell me is that we have two blocks, one bigger block of size s and one smaller block of size n square, and we need to find the number of times we can subtract the length of the smaller block from the larger block, right? And from this diagram, it is pretty clear that this is nothing but the greatest integer function of the division of the length of the bigger block by the length of the smaller block. And so it is pretty clear here that the answer is going to be nothing but the GIF of s divided by n square. And yeah, this is the entire proof of the problem. So all you need to do here is to see in s and n square and just simply output the value s upon n square, and that will give you the correct answer. Right. So this completes the solution to problem A. There is no need to look at the code here because it's just an O1 solution. You just need to output s upon n square. So let's move to the next problem now, problem B. All right. So here we are given a sequence of n non-negative integers, and initially all the sequence are unpainted. What we can do is we can paint each number either red, either blue, or we can also leave it unpainted. Okay. And for a color C, count of C is the total number of elements in the sequence that are painted in the color C. So count of red is the number of elements which are painted in red, and similarly for blue. Okay, so what we need to tell is we need to tell whether or not it is possible to paint the sequence in such a way that the sum of all the elements which are painted red is strictly greater than the sum of all the elements which are painted blue, and at the same time the count of all the elements which are painted red is strictly smaller than count of all the elements which are painted blue. Okay, so yeah, I think the problem statement is very clear in itself, so there is no need to further discuss it. All right, so yeah, let's try to look at the solution. This problem, I found it to be very simple. There is a very easy greedy algorithm here to solve this problem. So the requirement is that count of red should be strictly smaller than count of blue, and sum of red should be strictly greater than sum of blue. Okay, so this is what we want. So one thing which we can simply do here is that we can iterate for the value count of B. So this is the value on which we can iterate. So let's look at the algorithm. Very simple greedy algorithm here. So iterate on count of B. And now let's see how this simplifies our problem. So now we are iterating on count of B, but we are not just iterating on this count. We can also definitely say which elements we are going to take and which elements we are going to color blue. Why? Because we need to make sure that the count of red is smaller than count of blue, but at the same time we need to make sure that sum of red is greater than sum of blue. So let's say we have fixed that we are taking x elements as blue and we are painting the first x elements as blue, and then nothing is stopping us from minimizing the sum of blue, right? Because we need to make sure that the sum of red is greater than sum of blue. So if we are taking x elements as blue, then why not take the smallest x elements, right? Because that will make our sum of blue as small as possible, right? Okay. So first observation. So if we take x elements, if we paint x elements as blue, then we should always choose the smallest x elements, right? Okay, now let's look at the other condition. Now let's look at all the numbers which we are going to paint red. So let's look at the first condition. We need to make sure that count of red is strictly smaller than count of blue, but at the same time we need to make sure that sum of red is strictly greater than sum of blue. So what we need to do is we need to maximize the sum of red, and at the same time we need to make sure that its count is less than x, right? Remember that I am taking x elements as blue. Okay, so here nothing is stopping us from taking exactly x minus 1 elements as red, and that too the greatest x minus 1 elements. Why? Because simply I need to maximize this value sum of r, so why not just choose the greatest elements, and why not just choose the maximum amount of elements, which is x minus 1, right? So we will take the greatest x minus 1 elements and paint them red, right? And now what remains is to simply check whether these two conditions are satisfied or not. Obviously we are satisfying the first condition because we are taking x elements as blue and x minus 1 as red. Now all we need to do is we just need to check whether sum of red is greater than sum of blue or not, and that can be very easily done using prefix sums or maybe using 2 pointers or something like that. But that is just an implementation detail which can be made very clear during the code. So yeah, mainly the algorithm is very simple. We do this, we iterate on the count of b. If we are painting x elements as blue, then we will paint x minus 1 elements as red. Also we will take the x smallest elements as blue and the x minus 1 greatest elements as red, and that will be it. So let's just have a look at the code now. So the code is simple. First of all, we sort the array and we create the prefix sums, and these prefix sums will later on help us to quickly find out the sum of all the blue balls and the red balls. So yeah, if we are choosing the first I elements as blue, then we will choose the last I minus 1 elements as red. And so the sum of all the blue elements becomes prefix sum of I, and the sum of all the red elements becomes prefix sum of n minus prefix sum of n minus I plus 1. And finally we just need to check if red sum is greater than blue sum. If that's true, then our answer is going to be yes, and if we never find such a situation, then the answer is going to be no. Okay. So I hope this is clear enough. Now we will move on to the next problem. Problem C. Again, here the solution is really simple to problem C as well, but somehow a lot of people face a lot of difficulties, and also there were a lot of other algorithms which people tried, like greedily choosing the maximum value and stuff like that, but those things didn't work. So yeah, before that, let's just read the problem. So in this problem, a number is called powerful if it is a power of 2 or a factorial, right? A power of 2 is just a power of 2, and a factorial is nothing but factorial of I is nothing but the product of all the numbers from 1 to I. It is a very standard term in mathematics. So yeah, powerful numbers are powers of 2 and factorials. And now we have been provided with an integer n, and we need to find the minimum number k such that n can be represented as a sum of k distinct powerful numbers. So yeah, we need to find this value k such that n can be represented as, like, we need to find the minimum such value k such that n can be represented as a sum of k distinct powerful numbers, and that is it. Note here that the constraints again are huge here. N is up to 10 to the 12. So any kind of dynamic programming or stuff like that is probably not going to work. Okay. Yeah. So yeah, the problem statement is clear enough. Let's just look at the solution. The solution here is going to be small. There is a very short and crisp solution here. So the problem is that we can use factorials and powers of 2, and we need to reduce n to 0 using distinct values, right? So that's the problem. So before that, let's consider a very simpler problem in which factorials are not there. So what happens if we are only allowed to use powers of 2? Now, if factorials are not there, then this problem becomes greatly simplified, because this is a very, very standard problem. We need to represent the number n as a sum of powers of 2 and as a sum of distinct powers of 2. And it turns out that there is exactly one way to do that. and that is the binary representation of n, right? So binary representation of n. So that is going to be the answer. And so the answer is going to be nothing but the number of set bits in the binary representation of n. Okay. So yeah, if factorials are not there, then the answer is simply going to be the number of set bits in the binary representation of n. Now we just need to see what happens, what changes happen when we introduce factorials. Okay. So that's the problem. Now the main trick. The main trick here is that we will never use a factorial which is of a number which is greater than 15. Like we won't even use 15 because even 15 factorial exceeds 10 raised to the power 12. Notice that n is only up to 10 to the 12, and if you can actually easily compute these factorials using a calculator. So during the contest, the best way to think about it is that try to find out the maximum possible value of a factorial that we will use. That is what I did, and so I concluded that since 15 factorial is greater than 1e12, we will never use the factorial of a number greater than 15. Okay, so that's the main thing that you need to notice here. So now what you're left with is that you have 1 factorial, 2 factorial up till 15 factorial, right? So we have 15 numbers and we are allowed to use any subset among these numbers, right? We have 15 factorials and we are allowed to use any subset among these, right? And once we use this particular factorials, then we will reduce the number n by the sum of all the factorials that we used, and now we can only use powers of 2, and so for the remaining number we can just count the number of set bits in that number, and that will be our answer. But there are these 15 factorials and we can choose any subset among these numbers. But so how to tackle this? Well, you just need to use all the subsets. Why? Because there are simply just 15 numbers, and with the number as small as 15, it is possible to generate all the subsets. And that is because if you have a set of size x and you need to generate all of its subsets, then the time complexity of doing that is 2 raised to the power x, and 2 raised to the power 15 is not very large. If we calculate, 2 raised to the power 15 is nothing but 3 into 10 raised to the power 4, which is not a very large number. Since there are around 100 test cases, it turns out to be around 3 into 10 raised to the power 6. So we can easily do that within our time limit. So what we will do is that we will generate all subsets of numbers from 1 to 15 and iterate on all the subsets. So we will iterate on all the subsets, and what we'll do is that let's say we are on a current subset sub, and what we'll do, let's say we are on a subset S. Okay. So what we'll do is that we will subtract n, we will subtract sum of S from n, and now we have a number and we are only allowed to use the powers of 2, and so we will just take all the set bits in the binary representation of the remaining number, which is n minus sum of S. So now we will take the set bits in the binary representation of n minus sum of S. So in total, the total number of operations that we will perform for a subset S is nothing but the size of S plus number of set bits in n minus sum of S. And we will iterate on all the subsets, calculate this value and take the minimum over all the subsets, and that will give us our final answer, right? So that is it. That is the entire solution to this problem. Let's just have a look at the code. Okay, so we have numbers from 1 to 15. First of all, we calculate the factorials of all numbers from 1 to 15. This is a very standard thing. So factorial of I is factorial of I minus 1 times I. So this way you can do that. Now what we need to do is we need to iterate over all the subsets from 1 to 15. Okay, and how we do that? So there are many ways to do that. I'm not saying this is the only way. There is a very easy recursive solution to do that as well, but this is the way that I prefer. So we can use bit masking to calculate to iterate over all the subsets of a particular set. This is a very standard thing to do. What we do is we iterate our mask from 0 to 2 raised to the power n minus 1. Here n is 15, and we have a mask, and what we assume is that in our mask all the set bits are the elements which are in our current subset, and all the unset bits are the elements which are not in our current subset. And in this way there are exactly 2 raised to the power n elements, 2 raised to the power n distinct values of mask that we'll go on, and it turns out that there are 2 raised to the power n subsets. So we will essentially be going over all the subsets in this way. And so then we will iterate on all the bits, check whether a bit is set or not. If the bit is set, then that means that element is in our subset. So we add the factorial of that element to the variable sum, right? And this variable ppc is nothing but the built-in pop count of mask. Built-in pop count is a library function in C++ which basically gives the number of set bits in the binary representation of the parameter which is passed here. So here ppc represents nothing but the size of the set S. And finally, when we have computed the sum, if this sum is less than equal to n, then the value that we will get here is the number of set bits in n minus s, which is the built-in pop count of n minus sum, plus ppc, where ppc is the number of elements in the particular subset, right? And then we will just minimize answer with this value val. And we'll do this for all the subsets, and the code is as simple as this, and this will solve our problem. Alright, so this completes the solution to problem C. Now we'll move to the last problem that we'll be discussing today, problem D. So according to me, this is a very difficult problem. At least I found it to be very difficult, although it is rated only 2000, but I think it is a bit underrated. It should be at least a 2100 according to me. But anyways, let's try to solve it. So here we have a tree of n vertices numbered from 1 to n, and for each node, let wi be the weight of the ith vertex. Okay, so we are assigning a weight for every vertex, and there is this condition of a vertex being good. So a vertex is called good if the weight of this vertex is equal to the sum of weights of all of its adjacent vertices. Okay, if a vertex is called good if its weight is equal to the sum of weights of all of its neighbors, right? So initially all the weights of all the nodes are unassigned, and we need to assign a positive integer weight to each of the vertex of the tree such that the number of good vertices in the tree is maximized. Okay, so we need to assign the weights to all the vertices such that the number of good vertices is maximized. But also, if there are multiple ways to do it, we need to find such a way that the sum of all the weights of all the nodes in our tree is as less as possible. Okay, so the first priority that we have is to maximize the number of good nodes, but if there are multiple ways to assign these weights to the tree, we need to find such a way that it minimizes the sum of weights of all the nodes in the tree, right? Okay, so that's the problem. The problem statement is as simple as this. So we have a number n and we have the entire definition of the tree here, and we need to finally output the maximum number of good nodes and the minimum possible sum to get that number of good nodes. And in the second line, we also need to output the weights that we have assigned to each and every node. So we don't just need to output these two values, we also need to output a valid assignment, right? So yeah, that's the problem. Let's see how we can solve this. So there is just one basic observation that this problem is based on. So let's look at some cases. The first case is that n is equal to 2. We will just get rid of this case because it is just something which we have to do specially here. So this is a base case, and like this is an extra case here that we need to handle. So if n is equal to 2, we can easily see that there will be just one edge which will be between 1 and 2. We can see that here in the samples. And so if there is this one edge, we can just assign the weight of 1 to both of these nodes and get done with it. Both these nodes will be good. So the number of good nodes is 2, sum of weights is 2, and the assignment is 1, 1, right? So n is equal to 2 is a trivial case. So from now on, I will assume that n is strictly greater than 2. Okay. All right. Now, I'll make one basic observation that will be used to solve this problem. And that observation, or maybe I should write it as a claim, because later on I'm going to prove it as well. So the claim here is that two adjacent vertices can't be good. So two adjacent vertices can't be both good. Remember that a good vertex is a vertex which has a weight which is equal to the sum of weights of all of its adjacent vertices. So I am trying to make this point that two adjacent vertices can't be both good at the same time. Okay, and let's try to prove it. The entire solution is going to be based on this claim that two adjacent vertices can't be good, and this is the only restriction, right? This is the only restriction. Right, so let's try to prove it. So for the proof, there are two cases. Again, let's look at these two cases separately. The first case is that both of them have neighbors. So we have two nodes u and v, and so we have two nodes u and v, and we are trying to prove that both of them can't be good. So these are two adjacent nodes, and we are trying to prove that both of them will never be good. That is what we are trying to prove. So case 1 is that both the nodes u and b have neighbors. Okay. So let's see why this is true for this first case, and then we will look at and then we'll see the second case. So yeah, so now we are assuming that both the nodes have neighbors. So let's see how this thing will look like. So we have this node here u, and we have this node here v. Okay, so u has some neighbors and v has some neighbors. Okay, so the structure looks something like this. So let's say we assign x to u, and the sum of all the neighbors of u, the sum of weights of all the neighbors that are there of u, let's say that is nu. Okay, and let's say we assign y to v, and the sum of all the neighbors of y is nothing but nu. Okay, so we have nu and nv. And now let's see what happens if we try to make both u and v good. So first case is that u is good. So u is good, then that means that the sum of all the neighbors of u is actually equal to the value that we assigned to u, which is equal to x. So x is equal to the sum of all the neighbors of u. So this is the neighbor v, which has a value y, and the sum of all the other neighbors of x, which is nu, right? Similarly, v is also good. So that will give us another equation, and that will be that y is equal to x plus nv. Okay, so let's say this is the first equation and this is the second equation. So now what we'll do is we'll substitute the value of x from 1 into 2. Okay, so what we'll get there is that y is equal to, now notice x is y plus nu, so y plus nu plus nv. Okay, so this y and y will cancel out on, and we will get something like nu plus nu plus nv equal to 0, right? And notice that I have assumed that both x and y have other neighbors as well. So nu and nv will both be non-zero numbers, because all the weights are non-negative and basically non-zero and non-negative numbers. So all the weights are positive, right? Yeah, so we have to assign positive integer weights. It is clearly written here. So nu and nv both have to be positive, but here we are getting that nu plus nv is equal to 0, which is not possible if both nu and nv are positive. And so we have a contradiction here, right? So we have a contradiction. Similarly, so this is the first case, and then similarly we have a second case in which only one of them has a neighbor. Notice that it cannot be possible that both of them don't have neighbors, because if both of them will not have neighbors, then both of them will become an isolated tree, and that means that n is equal to 2, which is obviously not the case. So at least one of them will always have a neighbor. So case 2. So one of them has a neighbor. Only one of them. So now let's see how this is going to look like. Again, the situation is the same. We have this node U, we have this node V. So let's say V has neighbors and U doesn't have any neighbors. So this is U, and this U has an assigned weight of X. This is V. V has an assigned weight of Y, and the sum of all the neighbors of V is nothing but NV. Okay, and now we will try to make both of them good, arrive at two equations, and then arrive at a contradiction again. So if U is good, that means that X is equal to Y, right? Because the sum of all the nodes which are adjacent to U is just Y. And V is good, that means Y is equal to X plus NV, right? So using these two equations, again we will get NV equal to 0, which is not possible, right? So again we have a contradiction. So this essentially proves that two adjacent nodes can never be both good, and there is no extra restrictions that we have. So we have proved that two adjacent nodes can never be good. Okay. So yeah, this is what we have proved here. Now, with this fact in mind, we are now ready to apply the basic dynamic programming solution to this problem. So using this fact, we will apply dynamic programming, right? So now essentially what the problem here is, what do we include in the state of our DP and what the DP is going to represent. These are the two questions that you need to ask yourself, right? So one thing is that since two adjacent nodes can never be good, it makes sense to include in our DP a Boolean value which says whether or not this particular node is included in the DP or not, right? So that is important to be included in the state of our DP. And the other thing is that what the DP is going to represent, right? So notice here that we need to maximize the number of good nodes and we need to minimize the sum of all the weights. And so it makes sense to take both these two values and make our DP in such a way that our DP represents both these two values, right? So now we are ready. So let's try to define the DP. So what we'll do is we will create two DP arrays. So one DP array will look something like this: vector of pair DP1. So this will be storing nothing but the maximum number of good nodes and the minimum sum of all the weights. Let's say I. So DP1 of I is storing the maximum number of good nodes and the minimum sum of all weights if we, so in the subtree of node I, obviously, in the subtree of node I, if we choose to make the ith node good. So this is what DP1 of I will represent. And similarly, we will create another DP array, DP2 of I, and that will store the same values, but here we will try to make sure that this ith node is not chosen to be a good node. That is the only difference between DP1 and DP2, right? Okay, so we have another array DP2 of I which stores the maximum number of good nodes and the minimum sum of all the weights in the subtree of the node I if we don't choose the ith node as a good node, right? Notice that the idea of making these two DP arrays comes from the fact that we can't have two adjacent nodes which are good. So it makes sense to include this Boolean value whether or not the ith node is good or not into our DP. That is why we are creating two DP arrays where one of them is making sure that the ith node is good and the other one is making sure that the ith node is not good. Okay. Right, so now we have these two values and the transitions are not that difficult to understand. The only restriction we have is that if we choose the ith node to be good, then we'll go over all the children of the node I, and the only choice for all the children is that they are not good. Similarly, if we decide to choose the ith node to be not good, then there are no restrictions on the children and we can choose the children to be good or not good. Okay. So yeah, I think it will be better if I show the transitions using my code only. And yeah, so the transitions are not very difficult here. You can easily think about them yourself as well. So the only thing to make sure is that if we are trying to find the value dp1 of I, then we will go over all the children of the ith node and we will take the value dp2 of I or dp2 of C for all the children C. Similarly, if we are trying to find dp2 of I, then we will go over all the children C of the ith node and we will take the maximum value among dp1 of C and dp2 of C. Let me write it down also. So for dp1 of I, we go to all children. Also note here that I am arbitrarily routing the node at any node. It doesn't matter on which node we route the tree. So for dp1 of I, that means we are choosing the node I. We will go to all the children of I. Let's say a particular child is C and take dp2 of C. And for dp2 of C, dp2 of I, we go to all children C of I and take max of dp1 of C and dp2 of C. And this is because when we are deciding to choose the ith node as good, then any child of it can't be good because of the fact that we just proved. So we will only take dp2 of C. And if we are trying to find out dp2 of I, then that means the ith node is not good. Then there are no restrictions on the children. So we will take the maximum of dp1 of C and dp2 of C. Okay. So once we have calculated all these values, we have the answer to our problem. That is, we have the maximum number of good vertices and the minimum possible sum, and that is nothing but the best value that we will get among dp1 of root and dp2 of root, where we can choose any node to be our arbitrary root. Okay, but we also have to output the assignment of weights, and that is also again not a very difficult thing to do. What we can do here is that we can just launch another DFS, and in our DFS we can just recursively assign every node to be good or not depending on the values dp1 and dp2. So we will compare dp1 of I and dp2 of I, and if dp1 of I is greater than dp2 of I, then we will decide to make the ith node good. Otherwise we will decide to make the ith node not good. If dp1 of I and dp2 of I are both good, then it is our choice. We can arbitrarily decide to either make the ith node good or bad. But also there is one thing: if dp1 of I is greater than dp2 of I, then that means we have to take the ith node, but at the same time we can't take any of the children. So yeah, so if we decide to take the ith node, then we need to make sure then we don't take any of its children, and that can be done by just passing a boolean variable into the DFS function that we'll do. So that is just another implementation detail that we have. So let's just have a look at the code now. That will give us a much better understanding of the problem. Okay. So what we do here is we take an adjacency list, we take a DP array, and here instead of dp1 and dp2 as two separate arrays, I am just taking a 2D vector of size 2. And yeah, so what we do is, first of all, if n is equal to 2, we just get done with this base case. Otherwise we do a DFS and populate all the DP values. Let's see how we do that. Okay, right. Also notice that if we are trying to make a node good, then basically what we need to do is that we will try to make all of its adjacent node be equal to 1. And so we will assign the value of the size of the adjacency list of the node to our current node, and we will assign 1 to all of its neighboring nodes. Okay, so that's later on thing. So first of all, we do this DFS, and now we need to populate the DP value of our current node. Okay, so we have two choices: either we take this node or we don't take this node. Okay, so if we are taking this node, right now the number of good nodes will be 1, and the minimum sum that we'll get will be the size of adjacency list. I am multiplying the sum by -1, and the reason for that will become clear later on when we go to this assignment function. Okay, so and the second choice that we have is if we don't take this. So if we don't take this node, then the number of good nodes will be 0 and we will assign a 1 to it. So here I have a -1. Okay, so now I'll go to the adjacency list, and what I'll do is obviously if I'm taking it, then I can just take dpx0. Here dpx0 represents that I am not taking x. So if I am taking the current node, then I can't take the second node, then I can't take any of its children, so I don't have any choices. So I will just do take dot first plus equals to dpx0 dot first, and similar thing for take dot second. But if I'm not taking the current node, so if I'm trying to find out not take, then I have two choices. Either I take dpx0 or I take dpx1, because there are no restrictions on x right now, and I will take the one which is maximum, right? So if dpx0 is greater, then I will take that, and if dpx1 is greater, then I will take that. And finally I have my take and not take pairs with me. So dp cur node 0 means that not taking cur node, and dp cur node 1 means taking cur node. Okay, so yeah, these two variables will hold these values, and in this way we can just simply populate our dp values. And now what is left is to do the assignment. And to do the assignment, what we pass in our DFS is our current node, its parent obviously, and also a boolean function bad, which denotes whether or not our parent, the parent of the node which I am at currently, was assigned to be good or not. So if the parent was assigned to be good, then this boolean variable bad will be true, because if my parent is good, then I definitely have to be bad. Okay, so if I am bad, or if it is better to not take this value, that is dp cur node 0 is greater than dp cur node 1. In both these two cases, I say that good of my current node is false, and also this boolean variable f is false, because going down I don't have any restrictions on my children. Otherwise this boolean variable f is true, and also good of cur node is true. Okay, so now I go to all of my children and I continue with this assignment. And finally what remains is to construct the answer. So I will just iterate on all the vertices, and if my current vertex is good, then I will increment my answer. I will increment my sum by the size of the adjacency list, and also I will assign the weight to be equal to the size of the adjacency list. Similarly, if it is not good, then I will simply increment my sum and assign 1 to my current node, and I will just output my answer, right? So yeah, this completes the solution to this problem. I know this was a bit tricky to understand, but if you are not able to get this, I recommend you to go to my profile and have a look at this code. If you are still having difficulties, try to have a look at this code 2 or 3 times, and I'm sure you are going to understand what exactly is going on here, because it is basically a very difficult to understand exactly the transitions and stuff like that. But it is like, if you try to understand it yourself, I don't think it's going to be much problematic. Okay, so yeah, with this I complete this video, and this is all that I had planned for today. So thank you so much for watching, and I will see you in the next video.